Welcome to Section 3, Training a Supervised Learning Model. This is Lecture 10, Interpreting the Logistic Regression Model. So starting off reading in the same data again, doing the pre-processing that we've done a few times over. I'm going to be selecting the optimal model that I trained in the previous lecture. It's the one where I've explicitly weighted the classes. And once we've got this model and we've evaluated it, we think it performs well from a performance perspective. It classifies reasonably well what we wanted to classify, and in a lot of cases, particularly in credit risk, regulated industries, in some sense fraud as well, we are interested in understanding what the model actually sees. We desire some level of model interpretability. With more simple linear models, it's quite easy to interpret them, to know exactly why they made the decisions that they made, and which features contributed to which predictions effectively. But with some more complex nonlinear models, it does get trickier to interpret what the model is actually doing, although there are some approaches that allow us to understand what contributed to what decisions. And we can do that from a post hoc perspective, so we can see it after the fact, after the model's been trained, which features contribute most significantly to a model's decision. All right, so one of the first things we can do once we've got this model class in scikit-learn is to just use this dot classes underscore attribute that allows us to see, well, it's a binary classification model. We know this already, but this is just one of the attributes that are available to the train model. Then something else that we can look at is the model coefficients. So those represent the weightings or the significance or the importance of each of the features in that model's ability to detect fraud or not, effectively. So we can think in a very simplistic way of a simple linear equation where y equals mx plus c, c being our intercept, x being like a single variable of interest, m being our slope, which effectively is like the importance of the feature in that sense. If we extrapolate that to logistic regression, where we've got multiple features, then what we have, instead of this C term, which is our model intercept, where, if we make x equals to 0, what is the y value? So, the C, we're getting what we call beta 0, which is our intercept. Then for all of the other features in our model, so if we've got, feature 1, feature 2, in our case, we've obviously got quite a few features, but, in the sense that we've just got 2 of them, each of these features has their own beta weighting, which is a model parameter that is trained and updated during the model training process. Once that model converges and is finalized, we then have access to those coefficients. So we can actually just print this attribute dot coefficient underscore, and then we can actually see, which is interesting because we can actually pick them out, and those that have a a very strong positive value are models that are, or rather are features that are likely to be important and to contribute significantly to the detection of fraud. And they go both ways. They can scale from -1 to +1. And those that have a very, I guess, mild mid-range number that hovers around 0, those would be insignificant. So we could technically remove them. They might be redundant. But yeah, it gives us a good sense of what's actually going on. It gives us a good proxy for feature importance for the logistic regression model specifically. Then the intercept term, we can also retrieve that. So just by accessing the dot intercept attribute. Then another nice feature of the logistic regression model, as well as a few others in scikit-learn, is that you're able to determine the class probability. So not just the classification, whether it's a 0 or a 1. You can also see, well, for this first prediction, we can see the probability of that prediction being a 0 was 98.6%. And conversely, the probability of it being a 1 was 0.01%. So, or rather, that'll be 1.3%. So in this case, if our standard classification threshold, so where it makes that decision whether it's a positive class or negative class, if that sits at 50%, then this would, automatically flag the transaction as being good, non-fraudulent, because overwhelmingly it states that if there's a 98.6% probability that it is from that class. One word of warning though is that these models are not 100% calibrated, so it isn't a true probabilistic interpretation of class distribution. If you do want to recalibrate the models, then you can make use of the model calibration functionality within scikit-learn, and training something called an isotonic regression helps you to get there. So I've put a link to the URL here. You're welcome to try that out as well. All right, so in the case that we've got models that are, nonlinear, potentially neural networks, or models that don't have feature interpretability embedded within them out of the box, we can point to something called SHAP, which is a very well, I guess, understood and well used library. Within Python, there's a API available on GitHub that you're able to download. You can pip install SHAP and make use of it for all of your models. You can use them for your simple models as well as your more complex neural network models as well. So what is SHAP? SHAP is based on the concept of a Shapley value, which is the average expected marginal contribution of one feature within your set of features, after all possible feature combinations have been considered. So it looks at the contribution of your feature to the broader predictive power of the model by looking at different iterations with and without that feature. And the Shapley value helps to determine a payoff for all of the features, when each feature might have contributed more or less than others. So to get up and running with SHAP in Jupyter Notebooks, we can just import SHAP and then initialize it with this JavaScript widget, which allows us to print the output nicely in Jupyter. And once we've done that, we can initialize what we call the linear explainer, which takes as input our train model, which is just a logistic regression model, as well as the training data that we use to train the model. And then what it's going to do, it's going to look at the interactions between the model and the training data that was used to train the model in order to generate the summary plot, which I will explain below. Once we've initialized this explainer object, we feed it new data, and which is our input data, which can be test data, for example. And then we can apply this summary plot method by, again, supplying the Shapley values and the test data, and we get this summary plot effectively. And what it does is it ranks each of your features. Remember, our features have the V notation, in descending order, with the most significant feature from a SHAP value contribution perspective at the top. And then as you move down, the features become less significant. We've got a nice legend here that tells us, the feature value, whether it's high or low, and how you interpret it is, so for V4 perspective, remember we don't know what the feature actually means because it's been transformed via PCA and the name of the feature has been masked. But what it's telling us is that it contributes strongly, so it has a high SHAP values in cases where the feature value is high. So the higher the V4 the higher the feature value, it's contributing positively to the detection of fraud. Whereas with V14, the converse is true. So we've got, it contributes, it's got a high SHAP value, so it contributes significantly to model output, but where the feature is lower. And we're looking at this from a fraud detection perspective. So by contribution, it means contribution to detecting the fraudulent class. And V14, so the lower the value of the feature, the more it contributes to the detection of anomalies. So it's kind of the reverse. And then we can also see the distribution of all of the data points. And we can see if it's a lopsided distribution, if it's, very heavily balanced to one side, or if it's kind of more evenly distributed. And some, there's obviously a lot less variance in terms of their contribution, and others there's obviously a lot more.